Ready? Okay. So, good afternoon, everybody. So, we are going to start the new module today, which is biomolecular NMR. In the last course, we have actually discussed the various methods in NMR, 1D, 2D, and 3D NMR introductions in a very general manner. So this set of lectures will see the applications of those methods, in particular to biomolecules. And that's why this is titled Biomolecular NMR. Now, what are biomolecules? Of course, the most important biomolecule is water. I have not written there, but the most important biomolecule is water. 80% of your body is water. And all the other molecules, big and small, they are all floating in the water, in the environment of water. They carry out their functions in the water. And water also, you actually use it directly in the imaging technology. Imaging techniques like MRI, you will use directly the water signal. In other kinds of biomolecules, I've listed here the most important biomolecules here: nucleic acids. Then you have proteins. Nucleic acids contain the genetic information. The hereditary material, it gets transferred from one species to the offspring, and information is carried from one between the parents and the children, and so on and so forth. Proteins are various kinds of molecules. These are enzymes, or they can also be structural proteins. They are responsible for the variety of functions that are happening inside the cell, living cell. Carbohydrates are the energy source. The food we eat gets digested, and the energy comes from digestion of the carbohydrates. Proteins are functional elements. Carbohydrates are the energy source. The lipids constitute the so-called membranes. The membranes are the envelope of the cell. So it provides a compartment for the cell so that in a confined manner, confined environment, the efficacy of the functions becomes high. So if it were all floating in open, of course, the chances of one coming to the other and the coordination among them becomes difficult. So the membranes form a compartment, and inside those compartments, you have this entire set of molecules, and they carry out their functions. And we will see what all various kinds of functions which are there. Then we have small molecules, the metabolites. The small molecules like ATP, ADP, glucose, and various vitamins. All of these come inside your creatine, phosphates. Okay, all of these things are metabolites. And these are also the products which are generated after the degradation of the big molecules like the carbohydrates or any other molecule which is degraded. Then of course it will be forming smaller molecules. These are the metabolites. That in itself is a big field. Metabolomics is a big field wherein you actually monitor the metabolites, their variation, concentration variation, the structural variations to identify certain diseases. If there is any abnormality in their expression, if the abnormality in the function of a particular protein or a system, then you will see that reflected in the metabolites. So all of these are the important biomolecules. They all work in coordination in the environment of water. And then there's an intricate relationship between the structure and the function of these molecules, because basically all of these have particular kinds of structures, and it is the structure that determines what sort of a function a particular protein or other molecule can perform. What is the relationship between the structure and the function? That results in what we call as the area called as structural biology. Okay, so this forms an independent area in itself. So this encompasses all the different kinds of molecules. And biomolecular NMR deals with this area, structural biology, not only the structures of the molecules, but also the dynamics inside the individual molecules, how the structure is influenced by the dynamics, how the dynamics influences the function, and so on and so forth. These are the general features of the biomolecules. Okay, now there is a central dogma in molecular biology. What is molecular biology? Structural biology is a particular area encompassing the structures. Molecular biology deals with the functions of molecules, and therefore it is called as molecular biology. Okay, to identify the function in terms of the molecular architecture and the molecular interactions, and that's why area is called as molecular biology. And the central dogma in molecular biology is represented in this manner. DNA is the most fundamental molecule, which is the hereditary material. Okay, then from the DNA you generate another kind of a nucleic acid. DNA is a nucleic acid. From DNA you generated another kind of nucleic acid, which is called as RNA. Typically this RNA is called as messenger RNA, and the process of information transfer is called as transcription. All of these processes are very complex processes involving various kinds of enzymes and different kinds of coordinated efforts between the molecules, not only the DNA, but also the various kinds of enzymes and the various proteins. And DNA, as you know, is a very large molecule, with something about the billions of atoms, billions of Daltons, that is the size of this molecule. And RNA is a relatively smaller one. And the DNA codes for entire set of proteins in your cell, that is called as the genetic code. And from the code, the whole sequence of genetic codes represents a particular kind of amino acid, and that is initially it is converted into a RNA, that is called as the transcription process. So from the transcription, from the messenger RNA, you generate what are called as the proteins, and this process is called as translation. So you have a transcription process. The DNA is hereditary material. Its replication results in offspring getting the same kind of DNA from one generation to another generation. And inside each generation, of course, all of these functions go on. From the transcription, you produce the RNA. From the RNA, you get the proteins, and proteins carry out the biological functions. So this is called as the central dogma in molecular biology. So at the root of all of this is the structure of the individual molecules. How do we understand the function in terms of the structure of the molecule or the structure and dynamics of the molecules? This has been an area of research for more than a century. In the initial years, of course, and even now, of course, X-ray crystallography has contributed a lot in all of this. For the structure determination, X-ray crystallography has been a major force in elucidating the individual structures of molecules. Okay, and for that, in the case of DNA, also it was the same also is RNA. What do we know about these structures from these different techniques, and how do we use NMR to characterize these structures? And some things which are happening in solution phase, we use NMR. X-ray crystallography produces the structure in the crystal or in the fiber, things like that. And then NMR can also be used to determine the structures of molecules in solution phase and understand the dynamics of those molecules in the solution phase. So what do we know about these the structures? As I said, this X-ray crystallography has been in place for many, many years. NMR has come into this picture in the last 50 years. This has taken the field forward to a quite substantial extent. So first we will describe what do we know about these individual molecules in terms of the structures from X-ray crystallography. Okay, so here the major revolution happened in the 1950s, and there when they elucidated the structure of the DNA. These three gentlemen, Francis Crick, James Watson, and Maurice Wilkins. These three people got the Nobel Prize for elucidating the molecular structure of DNA, which helped solve one of the most important of all biological riddles. That is, how is the replication happening? How is the information transferred from one generation to another generation? How it is maintained? Because you see always the children represent the parents. They have some physical structures common in all of them. There may be some differences which can also happen due to various reasons, but by and large the information transfer happens from the DNA. So that is called as the heredity. So hereditary, that's why DNA is also called as the hereditary material. So that was possible to explain on the basis of the structure which was given by these three people. And what did they use at that time? They used what is known as fiber diffraction. Fiber diffraction, because this DNA is a very large molecule, as I said, nearly a billion Daltons, okay, more than billion Daltons, and so therefore it is a huge molecule. So, and it is not possible to dissolve this in solution. This appears as a fiber. So therefore, the technique that can be used for characterizing this is fiber diffraction, X-ray fiber diffraction. The resolution X-ray fiber diffraction is not very large, but however, the fiber diffraction gives you information about the symmetry in these molecules. Symmetry, from the symmetry, you can calculate what sort of a structure it may be by model building. And that is the ingenuity of the researcher to explore these symmetries and build a suitable model which can represent these fiber diffraction patterns. The top two things which I have shown here, these are the fiber diffraction patterns. You can see that these two are looking very different. And these are, both are of the DNA, okay, but they have different kind of features. And those features, eventually they calculated that one of them represents this feature, other one represents this feature, this kind of a structure. You can see here there are two helices here intertwined in both cases, but their topologies are slightly different. One is slightly longish compared to the other one, and their width is also different. So they built this model on the basis of some information these people had. With regard to the DNA, we'll come to that, what information they had and how did they build the model. But this is the kind of a structure which they gave. And the hereditary information is contained in this, in the sense that when the two chains which are represented here, they open up, and the new molecule is of, this is called the duplexes. Both are duplexes. Okay, one of them is called as the A DNA. This is called as the A DNA. This is called as the B DNA. Okay, this nomenclature is mainly because of the differences in their topologies and the structure. By and large, it is the BDNA which is present in measured amounts inside the cell. And there are two chains here, as you can see, which are held together by certain kinds of things which are called as the hydrogen bonds. They are certain hydrogen bonds holding the two chains together. And when they open up, they form single chains, and then the new molecule is synthesized inside the cell to make the DNA once more. To make the DNA. So therefore, when that happens, exactly identical.
Waiting time.
Exactly identical chain will be synthesized. Therefore, the information is then carried forward. This is what happens in the process of replication or in the cell division and so on and so forth. So when that happens, therefore, one chain opens up, another chain is synthesized, which is called the complementary chain on that same chain. So therefore, the identical DNA molecule is transferred from one species to the offspring. So this is how the hereditary information comes. And this was a major breakthrough because the structure of the DNA provided the basis of this, the biggest riddle as to how is it that offsprings are similar to the parents. So it became a kind of an identification factor now. You can actually recognize the individuals on the basis of their DNA. Today also you see the so-called DNA test. You do a DNA test to identify where you belong, who is your parent. So all of this is done by the DNA test, and the basis of that is here in this. So these two structures were the initial fiber diffraction patterns. From the fiber diffraction, you got these two structures. So, and therefore, this was such an important thing that these people got the Nobel Prize for this discovery. Okay, now let's go further. So that was the fundamental molecule, which is called as the DNA, and that constitutes what is called as the genome. The genome of every species is different. Basically, it is the DNA. When you say DNA, it is the genome. It is very long, and in each of these genome, there are short segments. The segments are called as the genes. The genes, what are the genes? Genes are small entities in the DNA which gets translated to a form of particular protein. This process is called as the expression. Ultimately, finally, it's called expression. But the process is, first the genome gets transcribed into what is called as a transcriptome. So if you take a particular DNA of any species, typically there are about 30,000 genes. That means typically there are 30,000 proteins or genes, which are not 30,000 proteins. 30,000 genes are there, and these will be transcribed into messenger RNA. I told you the RNA. The transcriptome is the set of all of those RNAs, mRNAs, which are generated from the DNA. So the DNA to RNA, this is called as the transcriptome. The set of all of this is called as, all of the RNAs is called as the transcriptome. So from the DNA you come to the transcript, from the genome you come to the transcriptome, and from the transcriptome you come to what is called as the proteome. The proteome means it is the set of all your proteins, all the proteins inside a cell. So you see here there are 30,000 mRNAs which are produced from the 30,000 genes inside the genome. But then of course from those 30,000 mRNAs you produce nearly 100,000 proteins. That is because certain kinds of processes happen, which is called RNA splicing and things like that. By combination of cutting and pasting of these mRNAs, you generate various combinations of these mRNA species, resulting in nearly 100,000 of these combinations, and that produces 100,000 proteins inside the cell. So typically a living cell will have 100,000 proteins. Some small, some big. So remember, again, let me repeat once more, the DNA has about 30,000 genes. But notice once more that the DNA, these 30,000 genes correspond to a small section of the DNA. That is only up to just about 5 to 6% of the DNA. The rest of the DNA is believed, it was believed that it is called as the junk DNA. But actually, we are slowly started understanding that it is not really junk DNA, it also has a role to play. Still a lot of research has to go on there to understand what is the complete role of this entire DNA sequence. But a small portion of this is carrying out all the functions inside the cell as much as we know today. Okay, then you have these 100,000 proteins. Now 100,000 proteins interact with the various RNAs and various other molecules which are produced, like the carbohydrates, the small molecules, this, that, everything, to carry out the functions inside the cell. And that generates what are called as the metabolome. The set of all small molecules inside the cell is called as the metabolome. So that is the set of all metabolites. Metabolites, how they change as a result of a function. Metabolic profiling, how it happens in a normal living system or a diseased living system, how does it happen? So therefore 40,000 there are endogenous and exogenous metabolites. So therefore all of these have a complex interplay among these various systems. The genome, the transcriptome, the proteome, and the metabolome. A combination of all of these represents what is called as the phenotype. See, every individual is different. Every individual is different. Although the DNA is the same, but the way the things operate inside the cell can be different, various different. Therefore, all of these together forms what is called as the phenotype. And then these are all influenced by your environment, the kind of food you eat, what is the age, what is the lifestyle, what is the drug, what kind of a disease you get. Depending on, all of these will manifest in changes in each of these species here. The DNA itself may not change, but of course there can be some mutations that will happen. These are called epigenetic mutations. That will be dependent on the food you eat, the environment you live in. All of these contribute to the modulations there. So this whole thing is called as the phenotype. So you have different kinds of phenotypes inside in our whole in the universe or in the planet. So all of these one has to understand. Now you see the thing has become very complex. So it is a large number of molecules which are large molecules and small molecules together, they are present inside our system. What kind of an interplay is there between them? How do we understand this? How does the environment influence? What are the conditions inside the cell? If you modify the conditions, what happens? Okay, does it get influenced by the diet? Okay, so what diet you eat? Often we talk about, say, okay, you should eat more proteins, we should eat more carbohydrates, and different people are different. So therefore, depending upon all of that, every species here gets modulated, and then we need to understand the whole of these systems. So this is quite a challenging problem, and surely the research has to go on at a much faster pace than what is going on today. And various techniques are being used. X-ray crystallography continues to be there. Now NMR has contributed a lot in this area. And our emphasis in this course of lectures is to focus on what NMR can provide us. How do we understand this? So in order to, before we actually go into that, we need to know the fundamentals of these structures, fundamentals of these molecules, of their molecular structure. What are the basic building blocks of these individual molecules? Okay, how the individual building blocks are attached to each other and develop into a macromolecule, large molecule, small molecule, and so on and so forth. So that is the thing first we will have to do. So in the first two lectures, basically, that is today, we will be focusing on that aspect of the molecular structures. Okay, so let us come to the fundamental unit of the DNA RNA backbone. So we said is a duplex DNA. I saw it is a two helices which are going. So it consists of a chain of small molecules attached to each other, and that is called as the chain. So the chain goes from one direction to another direction, and it consists of certain basic units which distinguish between the RNA and the DNA. So we call this basic chain which is running as the DNA backbone or the RNA backbone. What does it consist of? The backbone, what does it consist of? See here, this portion is the phosphate. This is the phosphate here, PO4 phosphate. And then this portion here, from here to here, this is called the sugar. This is the sugar, or is the ribose or the deoxyribose. There are two kinds of 5-membered ring. There is a 5-membered ring here. There is a CH2 group here. Okay, from here there is a CH2 group. This CH group gets connected to the phosphate here. There is a phosphate, then there is a CH2 group, then you have a 5-membered ring here, and then of course this continues in the same manner. And next unit of the phosphate, then the CH2 group, which is the 5 prime, then it goes in this manner. Okay, and then at this point there is a base attached. Okay, there are two different kinds of bases which are attached, but this whole thing forms one unit. From here to here it forms one repeating unit of the entire backbone. So this is called as the DNA backbone repeating unit. Now you see the nomenclatures here. So all these atoms are numbered in a particular manner. Okay, these ones are numbered. The sugar ring, the ribose ring. First of all, the distinction between the DNA and the RNA lies in the nature of the ribose ring. So the ribose ring is that a carbon here, oxygen here, is carbon here, and a carbon there. So these are numbered as C1 prime, C2 prime, C3 prime, C4 prime, and this is called as O4 prime. And here this carbon is called as the C5 prime. C5 prime is attached to this phosphate. This oxygen is called as the O5 prime, and the opposite of that, this one, which is called as the O3 prime. O3 prime is also present here, because O3 prime then connects to the next one. Okay, so we will see that down here. Now here, in this 5-membered ring, at the C2 prime position, there is an oxygen here, and there is an OH group here. If this oxygen is present, then it becomes a RNA. This is called as the ribose ring. It's called as the ribose. If this oxygen is present, this is called as the ribose ring. If this oxygen is not present, if there is only hydrogen there, then it is called as the deoxyribose ring. So this is the distinction between the DNA and the RNA backbone. Rest of the things are just the same, except of course in the bases also there is a small difference. There are two kinds of bases. There are what are called as purines and pyrimidines. Okay, we look at the structures of those ones. And the purines, there are two purines, A and G, adenine and guanine. There are two purines, and the pyrimidines are thymine and cytosine. These are two pyrimidines. In the case of RNA, in place of thymine, you have a uracil. So I will show you more of that again. So in those ones. And then from the C3 prime, the O3 prime is present here. All of these carbons have an oxygen. Okay, so you see this C1 prime is attached to this oxygen, and the same this C4 prime is also attached to this oxygen. This completes the 5-membered ring, and then it goes to the C5 prime. This C3 prime is attached to the oxygen here, and this oxygen is called as the O3 prime. This connects to the next phosphate. This connects to the next phosphate, and the O5 prime of this is the same as that here. Okay, it's same as that here. So this chain continues in this manner, the backbone. Now, in this one, I've also indicated all the various kinds of elements of the torsion angle. These are called as, you have the alpha, beta, gamma, delta, epsilon, xi. What are these? What are these? These are the so-called torsion angles. And this will of course come in the next one or two slides also. So these are all single bonds there. A single bond means there can be free rotation around those single bonds. So therefore, the geometry of this entire nucleotide unit will depend upon these various torsion angles. It will depend upon these torsion angles there. Okay, so this is the fundamental unit. So to repeat once more, you have a phosphate diester and the sugar ring backbone. So it's called phosphodiester sugar ring backbone. So that is the DNA or the RNA. Okay, let's look at that once more in this little bit more detail. I told you about the bases. First, let us see on the bases. What are the bases here? There are three pyrimidines. On the top, we have this pyrimidines there. These are pyrimidines. There are three pyrimidines. Okay, cytosine, thymine, and uracil. Cytosine and thymine are present in DNA. In place of thymine, uracil is present in case of RNA. Cytosine is present in both. So both are pyrimidines. Now these are the purines. The purines, there are two purines there, adenine and guanine. Okay. So the difference between these two is just this here. You have NH2 in the case of adenine, NH2 is present at this position. In the case of guanine, NH2 is present at this position. And in here, there is a carbonyl group here in the case of guanine, and there is no carbonyl group there. Okay, rest of it is the same. This is the basic difference between these two. And then as a result of this, you will see there is an NH proton here, which is not present in the case of adenine. So this makes a fundamental difference. There will be two protons in the case of adenine. There is a H here and a H there, whereas here you will have only one H at this point, apart from the NH2, the NH2 and the NH. NH2 and NH, these are what are called as the labile protons. These exchange with water, and the CH protons do not exchange with water. So therefore, those ones will be observable in your NMR spectra. Even the CH, NH2 are also observable, but you have to record the spectra in H2O. Okay. Now, below here, I show the same structure once more in the what I showed you in the previous one. You have this ring here, 5-membered ring. This is the deoxyribose or the ribose ring. Okay, in the case of deoxyribose, there is no oxygen at this point. These are both hydrogens. In the case of ribose, see here, ribose, there is an oxygen here, OH, OH in these two, whereas in DNA, this is H and H there. And the CH2 is attached to phosphodiester here. This is the phosphate. Okay, so this is an expansion. These two are for the expansion of this sugar ring. Call it as a 5-membered sugar ring. It can be deoxyribose or ribose. And the ribose has OH at the C2 prime position. This is called the C2 prime position, which indicated to you. And this is the C3 prime position. And the chain continues as 5 prime 3 prime in the direction 5 prime 3 prime. Okay, that is shown here. So you have this 5 prime carbon here, and here is the 3 prime carbon. The chain continues in this manner. Therefore, and the bases at every sugar ring can be different. See, in this case, it is shown, the guanine is shown here. This is the 2 prime carbon, the 3 prime carbon. At the 1 prime carbon, the base is attached here. Okay, this base. Base can be any of these. It is the sequence of the bases that determines the information in your DNA backbone. So as you are having 1, 2, 3, 4, you go from the 5 prime to the 3 prime end, continuous go from 5 prime to 3 prime. You have the first one, then you have the second one, then the third one, and the fourth one. You continue in this manner, various nucleotide units. At each point, you have a base. Okay. And the sequence of these bases is the information content in the DNA chain. And that is why it is called as the hereditary material. This gets conserved. This information is conserved. The sequence of the bases is like your alphabets, okay? The 4 alphabets. There are only 4 alphabets, A, T, G, C, okay? And or A, U, G, C. So these are the structural elements of the DNA chain. Okay. More explicitly here, with regard to the structure, the chain direction goes from the 5' to the 3'. So we label here I minus 1, I plus 1. This is one unit to show if this is the I. The previous one is called as I minus 1. This is called as I plus 1. And the direction goes from the 5' to 3'. On this side is the 5' end. This side is the 3' end. Okay. So that is indicated here. See, the chain direction is this way. This is the 5' end. And this is the 3' end. Now, and the base is attached at this point. Now, there is also a single bond here. This is at the 1' position, there is a single bond which connects to the base. Okay. And there is a torsion angle there, of course, because if there is a single bond, there is a free rotation possible over there. So what kind of a rotation angles are present there? So that determines the relative orientation of the base with respect to the sugar ring. Now, let us look at the definitions of all of these various torsion angles. So the alpha torsion angle is defined in this manner. O3' I minus 1 P O5' C5'. O3' P O5' C5'. Okay, so there is this torsion angle. So this torsion angle determines the relative orientations of the O3' atom and the C5' atom. That is the alpha torsion angle. Beta torsion angle is the next one. Beta torsion angle is P O5' C5' C4'. P O5' C5' C4'. That is this torsion angle there. Okay? That is this. So similarly, you have here, you have here, you have here, and you have here. All this. This determines the gamma torsion angle is O5', C5', C4', C3'. Gamma torsion angle is this: O5', C5', C4', C3'. And delta torsion angle is this C5', C4', C3', and C2'. C5', C4', C3', and C2'. Notice here it is defined with respect to the C2', that is coming here on this side. You can also define it with respect to the O3'. Instead of going here, you also do it here in the along the side. There is only a small angle relationship between the two. There's certain constant one has to add. There is a small difference because these are not independent. Whatever is the value here, depending upon that, there will be a different value here slightly. So therefore, that can be defined in either way, defined in that manner also. And the xi torsion angle, the C3', O3', Pi plus 1, O3', I plus 1. That P is now, this P belongs to the next nucleotide unit. Okay, so that is C3', O3', C3', O3', P, and O3', I plus 1. That is the next one here. I plus 1, and then it goes on to this. This should be the yeah. C3, this should have been O5'. Yeah, this is it. Should be O5'. This comes down here. See, that is indicated here. Okay, it's in this manner. So that is basically the definition of the individual torsion angles. Okay, so now more explicitly in the colored manner with regard to oxygens you represent in red color. Okay, carbons are represented in the gray color. You represent the nomenclatures are also given here. C1', C2', C3', C4', O4'. Then the C5' here. Then the 5' OH that is attached to this. There is O and then the hydrogen here. Then the C3' oxygen and then the hydrogen here. That is the stick diagram in this to make it more clear. So this is the 5-membered ring. Then you have the O3' goes to the phosphate there, and this is the C5', O5'. Then it goes to the next one over there. P goes to the P. Okay. So the wireframe view. So these are different kinds of representations to enable understand the structures in a clear manner. Okay. Now, the nomenclatures in the basis, this is also important. Why we have to understand all of this? Because often we'll be talking with respect to the various kinds of numbers when you're looking at the NMR spectra. And therefore, the nomenclature of these things becomes important. Which atom is called what? With what number? So you see here, typically, if you take the adenine and the guanine, this position is called as number 1. Then the numbering goes like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. Numbering goes in this manner. Same is true in the case of guanine. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And in the pyrimidines, it starts from here, this NH, 1, 2, 3, 4, 5, 6. Notice here, this is going in this direction. Here it was going in this direction. These are typical rules in chemistry. You have this particular formula and the ways of numbering these ones. And the thymine also goes in the same manner: 1, 2, 3, 4, 5, 6. And uracil, 1, 2, 3, 4, 5, 6. And notice in the case of cytosine, you have an NH2 group at 4 position, and in thymine you have the NH group at 3 position, and there is a methyl at the 5 position there. Okay, in cytosine you don't have a methyl there. And in uracil, it is very similar to the thymine, except that you don't have the methyl. There is a proton in this case. Uracil has a proton there. Although both of them have 2 carbonyl groups, both thymine and uracil are 2 carbonyl groups, but the uracil does not have the methyl that is present in the case of thymine. This becomes extremely useful in analyzing the NMR spectra. So these are the color diagrams of the same structures which are given there. Okay, so these are the 5 different kinds of bases. Okay, what happens next? Now, adenines and the guanines, it is again the color picture of the same, of the thymines and the cytosine here, and the adenines and the guanines there. The purines and the pyrimidines down here. Okay, so the methyl group is indicated here. You can see CH3, there are 3 protons there, whereas adenine has 2 hydrogens here, and non-exchangeable hydrogens. These 2 are non-exchangeable hydrogens. The guanine has only 1 non-exchangeable hydrogen at C8, that is called as the H8, and at the H2 position, here you have an NH2 group there. This becomes an exchangeable proton. Okay, all the blues represent the nitrogens here, and the gray ones represent the carbons, and the white ones represent the protons. Okay, so N1, N3, N9, N7, these are the nitrogens. Okay, and N1, N3, N9, N7, and the NH2 there. And the oxygens, the carbonyl group is represented at C6 in guanine, and in thymine you have the C4 and C2, there are carbonyl there, and in cytosine, C4 you have the NH2, C2 you have a oxygen carbonyl group there. Okay, so the primary structure I have already mentioned to you how the chain grows. So this is the 5' end, this is the 3' end. Okay, phosphate bonds link DNA or RNA nucleotides together in a linear sequence. The 3' 5' phosphodiester bond. Okay, so this is this is the 5' here, and this is the 3' here. So 3' to 5'. So this goes in this manner, comes continuous like this, right? This is the 5' end, and this is the 3' end. And then you can see here in the bases here, I put 4 different bases here. Okay, and this one is a thymine. This is thymine, and this is what is this? This is guanine, and this one is cytosine, and this is adenine. See, the 4 different bases are put on the 4 different nucleotides. So the chain can continue like this. You can generate a large chain and with various combinations of these, and that is the information, as I mentioned to you, in the DNA sequence. That is the hereditary information. The sequence of the bases which are there is the information content of the DNA. Okay, so this is once again the color picture of the same, how it goes. In previous case, of course, it is a schematic. Now you see you start adding some structural features to it. It is not a linear thing like that. It has a structure. So they are all oriented, certain relative orientation with respect to this. And this happens because of the various torsion angles which I mentioned. Along the backbone, there are various torsion angles. The sugar ring also has various torsion. What happened?
No, sir.
Okay. But it is displayed here. The sugaring also various torsion angles. You have the four bases, the bases here C, G, A, T, the five bases there, and the relative orientations of all of these actually gives the structural features of the DNA sequence. Okay, this can vary from base to base, from individual to individual. Small differences will be there, not very large differences, but small differences will be there. What distinguishes primarily from one DNA to another DNA is the sequence of the bases. Okay, now the next important thing is how are the two chains? I mentioned to you that two chains are held together. In the original fiber diffraction data, there were two chains which were held together. And these are held together by the hydrogen bonds between bases. It turned out that the C always pairs with the G, T always pairs with A, and vice versa, of course. G always pairs with the C, A always pairs with the T. In fact, this was the information which was available to this Watson and Crick before they built the model. They knew that the number of A's is equal to the number of G's. When they did this analysis of the compositions of the DNA material, they always found that the number of A's is equal to number of T's and number of G's is equal to number of C's. Therefore, there must be some kind of a feature which maintains the equality of all of these things. These are called as Chargaff rules. Chargaff was the one who actually demonstrated this, and he said, okay, number of G's is equal to number of C's, number of A's is equal to number of T's, and that provided a great hint for them as to how this must be happening. So these are held together by kind of a hydrogen bonding base pairing. This process is called as base pairing. A C is held together, is paired to a G, and this is called a CG base pair. And a T is paired to A, and that is called as the TA base pair or the AT base pair. And one chain is running in this direction, the other chain is running in this direction. They are running in opposite directions. In the two chains which are there, the two chains run in anti-parallel fashion. Okay, so if we have this is the 5' end, this is the 5' end, here is the 3' end. In the other chain, this will be the 5' end and this will be the 3' end. The two chains run in an anti-parallel fashion. Okay, and then they are so disposed that the T and A pair, G and C pair, C and G pair, and AT pair and GC pairs, like that. Okay, this is the schematic. This is the schematic how this kind of a base pairing scheme happens. Okay, now you introduce structure into it. Okay, so same thing repeats. Now you see the chain is not just running in a straight way, in a straight line. They are actually forming helices. Each of these chain forms a helice. This is what I showed you in the original fiber diffraction structure also. That there are two helices which are running. Two helices. There are two helices here. One helix which goes like this. The second helix which goes like this. For the first helix, the 5' end is here. 5' end is like this coming. And the second helix, the 5' end is here. It goes in the opposite direction and it goes like that. So when it happens, then of course the base pairs are positioned. The bases are positioned conveniently so that they can form base pairs. So therefore, it's an intertwining of two helices. Intertwining of two helices which provides stability to the two DNA chains. And when these ones happen, there are other features which are also contributing to this chain, to the stability, and that is the so-called stacking of these bases. You notice these were aromatic rings. By and large, these purines and pyrimidines were, apart from the nitrogens which were present oxygens, but by and large these were close aromatic rings. You have the purine ring and the pyrimidine rings have aromatic rings. So therefore, there are stacking interactions between these base pairs. So one stacks over the other stacks over the other, things like that. This provides the stability to the DNA duplex or the RNA duplex. Okay, so hydrogen bonds hold together the two chains in a complementary fashion that also provides stabilization energy, and the resultant stacking of the bases provides additional stability to the DNA chain. And as a result of this, you will see there are some grooves. One will define certain grooves here. One defines what is called as the major groove and the minor grooves, and that is often well defined in the case of bDNA, but not so well defined in other kinds of DNA. There can be variations in the structure depending upon what sort of a variation happens in the DNA backbone or the relative displacements of the bases. Okay, what are the kinds of, what is the length from one to the other? How much is one full turn? See, for example, if I go from here to here, goes to here, then it continues from there, right? So this represents one full turn. And from here to here it goes, then now again it starts going like that. Okay, so therefore this is called as the one full turn of the DNA duplex. Okay, so how much is the DNA duplex? What is the height of this one? How many base pairs are required in this one? So what is the repeating unit? That is what gets reflected in your symmetry. In your X-ray crystal structures, if you are doing, when you look at the symmetry, it tells you what is the repeating unit. Okay, how much is the symmetry? And so that is what is the information which comes from the X-ray crystallography. Okay, so now let's look at more explicitly the base pairs. So here in this case, the wire frame, the AT base pair. AT base pair, in the previous one I showed you, these are okay there. Here I showed you here. The AT base pair has 2 hydrogen bonds and the GC or the CG base pair has 3 hydrogen bonds. Okay, now how do these base pairs occur? In the case of A, see there is this position is a NH2. This is the NH2 here. And the T oxygen is here and there is the N here. So, and this is the N here. So this NH pairs with this nitrogen here. And here the NH2 pairs with the oxygen. Therefore, this is the NHO hydrogen bond in the case of AT, and this is the NHN hydrogen bond. So there are 2 kinds of hydrogen bonds. In the T, there are 2 hydrogen bonds, AT pair. One of them is the NHN hydrogen bond, that is from T3NH to the N1A1NH. Okay, or N. And in the case of this is the space filling model. We will now look at the space filling model here. So in the case of the GC, there are 3 hydrogen bonds. The 3 hydrogen bonds, which are these, you can see from the colors. These colors indicate that. But the red color indicates there is an oxygen there. Okay, and the yellow dots are indicating the hydrogen bonds. The sticks are the hydrogens, individual hydrogens, and the carbons there. Okay, now the blues are indicating the nitrogens there, right? So in the GC, what hydrogen bonds you have here? In this, you have the NH2. This is the NH2 group. NH2, one of the hydrogens pairs to this oxygen here. So therefore, this is the NHO hydrogen bond. This one is the NHO hydrogen bond. And this one here is the NHN hydrogen bond. And this is here the NHO hydrogen bond once more. Okay, so therefore there are 2 NHO hydrogen bonds and 1 NHN hydrogen bond in GC, whereas in AT there is 1 NHN hydrogen bond and 1 NHO hydrogen bond. Okay, so this is the kind of a schematic which they built. Is that the only way they can form hydrogen bonds? No, we will see. There are many more ways we can form hydrogen bonds, but this model actually was miraculously successful. The way they built it, this Watson and Crick, and this became absolutely a novel thing. Intuitively was a great achievement. But there are many other ways you can form hydrogen bonds, because the reason is there are so many hydrogens, so many nitrogens, so many oxygens. Depending upon which nitrogen, which oxygen you use, you will form different kinds of hydrogen bonds. That will come a little bit later. Okay, so that is the structure of the DNA backbone and the base pair, how the duplex is held together. Now we have to look at further details about the various torsion angles. The torsion angles determine the backbone geometry, right? Torsion angles determine the backbone geometry. What are the components of the torsion angles? These are the alpha, beta, gamma, delta, which I mentioned to you. Those are along the backbone. But the sugar ring itself, see here, there are 4 torsion angles inside here. Okay, nu0, nu1, nu2, nu3, and nu4. Each of them, because they are all connected with the 4 bonds, 4 atoms. This is one. As you can see, nu0 is C4 prime, C4, nu0, C4 prime, O4 prime, yeah, C1 prime, C2 prime. That is this. This is nu0, right? And the nu1 is this. Nu1 is O4 prime, C1, O4 prime, C1 prime, C2 prime, C3 prime. That is new one. And nu2 is C1 prime, C2 prime, C3 prime, C4 prime. Clearly, of course, all of them are not independent, but these are four torsion angles one can define. And the nu2 is C1 prime, C2 prime, C3 prime, C4 prime. Nu3 is C2 prime, C3 prime, C4 prime, O4 prime. And also you can define a nu4, which is C3 prime, C4 prime, O4 prime, C1 prime. So there are five torsion angles you can define there. But of course, all of them are not independent. How do we know that they are not independent? Okay, now let's look at this. This ring is having five atoms. If there are five atoms, from chemistry we know that it will have 3n-6 degrees of freedom. Okay, and the sixth number comes because of 3 translational, and of course the n3 rotational coordinates have to be excluded. And then you define these remaining torsion angles in terms of the internal variables, internal parameters, and these internal parameters are n-1 bond distances, n-2 bond angles, and n-3 torsion angles. Okay, these ones are the independent variables one can have, degrees of freedom. Okay, bond distances and bond angles, of course you cannot change them too much. The thing that changes significantly are the torsion angles. Now torsion angles n-3 meaning what? There will be 2. N is 5. If n is 5, there are 2 torsion angles. However, that is the case when the molecule is not closed ring. But if you have a ring closure, it adds one more restriction. Therefore, it takes away one of the degrees of freedom with respect to the torsion angles, because you have to have the O4 prime completing the ring. So there is important consideration. The ring closure puts in another constraint. Therefore, effectively, you have only one torsion angle which is free. 1 degree of freedom with respect to the torsion which is free, and that is called as the pseudo rotation angle. That is represented by P. And in this way, with this equation, you can see this particular angle, which is called the pseudo rotation angle. This connects all the various torsion angles. You can describe the individual nus which are described here in terms of this P. The P can vary from 0 to 360. P can vary from 0 to 360, okay? And delta is a fixed number, which is 144. And tau m is the thing which actually defines how much the ring can be distorted. Whether all the 5 atoms are in the same plane or one atom in the 2 atoms are out of the plane. Typically, you can have 3 atoms in the plane. You can define a plane when you have 3 atoms. And the other 2 atoms, where do you place them? Either you place them in the same plane or you put them outside the plane. You can in principle do that. So depending upon how you place the other 2 atoms, you generate various kinds of structures, sugar ring structures like this. Okay. So in this case, if the C2 prime is up, C2 prime is up, C3 prime is down. This is a little down, this is more down here. Here the C2 prime is little up, C3 prime is more down. And here you have all of this. And this class of structures are called as the S conformations. And this sort of structure here, the C3 prime is up, 2 prime is down, C3 prime is a little up, 2 prime is similarly down, and the C3 prime is a little up, 2 prime is more down. Suppose what we have done here, we have considered the other 3 angles in atoms to be in the plane. Which atoms? We have considered the C4 prime, O4 prime, C1 prime. C4 prime, O4 prime, C1 prime, you consider these 3 atoms to be in this plane, and that is defined as the horizontal line there. And you are placing the other 2 atoms, the 2 prime and the 3 prime, with respect to that plane. So these are, depending on which one you put up and which one you put down, you generate a different kind of a sugar geometry. Okay, and that is described in terms of the one variable which is called as the pseudo rotation angle, that is P, and P can take various values from 0 to 360, 0, 180, things like that. Now, depending upon the value you have and what does the tau m define? Tau m defines how much is the sugar pucker, how much it is outside the plane, how much it is outside of this plane. That defines the pucker. That is a fixed number. That is typically about 38 degrees. And the P goes from 0 to 360. Okay. Now, you translate these values of various P's, various values of P into this structure, this kind of structures which are indicated here, and we generate various kinds of nomenclatures for the sugar geometry. So from here you go from C, endo means the thing which is on the side of the C5 prime atom. what is on the side of the C5 prime atom, and that is called as the endo. So if what is on this C5 prime is here up. So what is present here is the endo conformation. What is present on the down is the exo conformation. So you have the endo and the exo nomenclatures. What is up there towards the C5 prime is endo. What is down is exo. So therefore, if you take the P goes from 0 to 360 as I mentioned, you have 0, the nomenclatures are given here. 0, 36, okay, 72 and various kinds of things. Depending upon that, you generate different kinds of displacements of the 4 atoms. And we call them as C3 prime endo, C4 prime exo, O4 prime endo, C1 prime exo, C2 prime endo, C3 prime exo, and so on and so forth. All depending upon which atom goes up, which atom comes down, you have different nomenclatures for all of these. And so therefore what we say is things which are on the lower side of this, that is from here to here, all of these which are present, these are called as the south conformations. They are called as south conformations. The ones which are present on this side of this, which is called the so-called the north conformation. These are the north conformations. Okay, and it turns out that DNA has basically south conformations and RNA has north conformations. You can also have a certain kind of a DNA where you have the north conformations. This is a special case which we'll have. But by and large in DNA, you will have south conformation. That is S conformations. That is the C2 prime geometry or the mixtures of those. There are also twisted conformations. These are twisted ones. Some because one up, one down. These are called as twisted conformations. And those ones are mixtures of endo and exo. Shall we take a break here?
Yeah, you can.
Ah.
Short break, then
I will take a small break. Yes. So as I said, the first lecture goes for today.
okay.
One will go for today, and 2 will go for Friday.
Okay. So any doubt at this point? Sonny, you can write in the chat box. Any doubt at this point? Only T, huh? Huh? T-U-B-T. U-D-T. T-U-U-B-T. B. No doubt. Some questions, sir.
It's very tough for me. Who is it?
Who is that?
I can ask what is tough?
Hello, Tapas. Hello, Tapas.
Is it Tapas who wrote that?
Yes, I think, yeah. Uh, what is structure actually? Sir is describing how the molecular structure is, DNA structure is, how the base pairs are associating. So little bit you have to go to the.
So he is talking about the last portion. We will repeat that. Last portion is the sugar ring.
Okay. Okay, sir will be repeating that part. I think that this
circle. Pseudo rotation.
Could not follow properly.
Did not follow. Enter chat message here.
YouTube also you can check and it out coming. Just check. Just any doubt question mark करके छोड़ दो इधर ना.
Yeah, any doubt? We'll put a question mark there after any doubt.
Right, any doubt and then question mark.
Any doubt का spelling क्या लिख रहे हो तुम? BT. हाँ, बस.
Just wait if someone is asking. So your NMR analysis, you will be using those symbols.
Yeah, that becomes very important.
Yeah,
So this nomenclature becomes very necessary.
necessary. Yeah.
So again and again we'll talk about this 1 prime, 2 prime, 3 prime. All of them we'll talk about it again and again.
Yeah, you can start.
Okay. So let me repeat this part of the sugar ring conformation. And it's a little complex, but one can, if you go, give attention slowly and you can follow it. It is not at all difficult. It is, see, we have a 5-membered ring. What we are facing the situation here is, you have a 5-membered ring here. 5-membered ring has how many atoms are there? You have, okay, let's take a chain of 5 atoms, O4 prime, C1 prime, C2 prime, C3 prime, C4 prime. Suppose they were in the linear chain. So if I have a linear chain like this, 1, 2, 3, 4, 5. There are 5. There is one atom here, 2, 3, 4, 5. Okay, forget this. So these 5 atoms, if I want to place some relative with respect to in a relative manner, how many degrees of freedom do I have? We can't have a chain here. Any 3 atoms, you can put them in a plane. Okay, that you understand. Any 3 atoms, you can put them in a plane. Now, other 2 atoms where they are present, and that will be determined by what kind of a degrees of freedom do you have, or the relative positions of all of these 5 atoms. What are the parameters? What are the degrees of freedom? So you have, as I said, for the 5 atoms, there are 3 minus 6 degrees of freedom. If n is 5, there are a total of 9 degrees of freedom which are there. Out of that, you have n minus 1 bond distances, that is 4 bond distances. N minus 2 bond angles, that means 3 bond angles for the 3 atoms. At every step you have a bond angle. And then you have n minus 3, 2 torsion angles which are sufficient. That makes it 9. N minus 3, you have 4 here, 3 here, 2 here. So that is 4, 3, 2. So these degrees of freedom are there. Now, that is if it is a linear chain. Then with this we can place all the 5 atoms appropriately in space. However, in this particular case, we have an additional condition. The additional condition is that the ring has to be closed. So this has to come back and join here. So that is an additional condition. And that means 1 degree of freedom is removed. You have therefore only 1 degree of freedom which is left to define the positions of all the 5 atoms. Because you cannot change bond distances, you cannot change bond angles, which are very hard, because it takes a very huge amount of energy. But these are small energy differences. These energy differences are of the order of few kilocalories per mole. The bond angles and bond distances, these are actually several, 100 kilocalories per mole, things like that. So you cannot change those. So the three-dimensional structure will be affected by the, or the stereochemistry will be affected by the torsion angles. And these are small energies. And this is determined by the torsion angles. Okay, and that's called as the puckering. It's called as the puckering of the sugar ring. How the atoms can be placed outside the in the relative orientations. Now, in that context, we can see 3 atoms can be placed in one plane, and we look at the other 2 atoms how they are disposed with respect to this plane. They can be above the plane or below the plane, or one can be above the plane, one can be below the plane. Okay, or they can all be in the same plane. All these are possible. All these different possibilities had to be represented by 1 degree of freedom, and that is called as the pseudo-rotation angle. That is called as P. Once this P is actually then can be related, we should be able to relate this to the individual torsion angles. Once I have a particular value of P, it must reflect a particular orientation of the 5 atoms. That means a particular combination of these torsion angles. Okay, therefore one particular value of P must define me all the 5 torsion angles. All the 5 torsion angles, nu0, nu1, nu2, nu3, nu4. Therefore all these 5 are not completely independent. They are dependent only on one, and that is the pseudo-rotation angle P. Once I define a value of P, I can calculate the individual nu0, nu1, nu2, nu3, nu4, which defines the positions of all the 5 atoms in the sugar ring. And that is given by this. Okay, the nu I is equal to tau m cosine P plus I minus 2 delta, whereas delta is equal to 144. This calculation has been done. This is the formula which is there. By putting a particular value of P, you can find out what the value of nu I should be. Supposing I put P, nu I is equal to 0. Okay, so P minus 2 delta. Okay, that becomes nu delta. Nu1 becomes P minus delta. Okay, nu2 P plus delta. If it nu3 P plus delta. Nu2 is P only, okay, because 2 minus 2 cancels. Nu3 is P plus delta, and nu4 will be P plus 2 delta, and the cosine of that, because P is a one particular value. I will not change that. For one particular value of P, what is the, depending upon what I have, I define all the 5 torsion angles here. I keep changing from 0 to 4. P is fixed, and therefore I get various values of nu0, nu1, nu2, nu3, nu4 I get for one particular value of P, and that will define the positions of the 5 atoms in the sugar ring, relative positions of the 5 atoms in the sugar ring. Okay, the maximum tau m is called as the maximum pucker. How much it can go out? What it will be dependent upon? It will be dependent on what is the maximum bond distance one will have, what is the bond distance one will have, because bond distances are fixed, we cannot change that. So therefore, they cannot be indefinitely, any arbitrary value of tau m is not possible. There is only a particular value of tau m is possible, and that is typically, it turns out to be about 38, okay, 38 degrees. So it can go up by 38 degrees above in the plane, and you have all the other values can be calculated in this manner. Now, you represent this schematically, all these various relative orientations in a kind of a circle, because P goes from 0 to 360. P goes from 0 to 360, and that will generate a whole lot of sugar torsion angles, whole lot of combinations of the nu0 to nu4. P is an independent variable, remember. P is one independent variable. I cannot put a restriction on that you should only go from 0 to 180. It can go from 0 to 360. There's one independent degree of freedom. So that degree of freedom can go from 0 to 360. So depending upon what value it takes, you generate different combinations of nu0 to nu4 that results in different disposition of the atoms in the relative dispositions of the atoms. Therefore, when I go from in the pseudo-rotation angle from 0 to 360, what sort of structures I get for the sugar ring? and those are represented by this particular nomenclatures: C3 prime endo, C4 prime exo, O4 prime endo, C1 prime exo, C2 prime endo, C3 prime exo, C4 prime endo, O4 prime exo, C1 prime endo, C2 prime exo, and so on and so forth. And endo exo means, I already have explained to you, endo means if the particular atom is towards the 5 prime atom, because the 5, remember 5 prime atom is outside the ring. 5 prime atom is here, it is outside the ring, it is going up here, you see, 5 prime is outside. Okay, if the atom is outside the is towards the C prime end, then that atom is called as endo. Anything that is below on the opposite side of the ring, that is called as the exo. Therefore, different combinations of nu0 to nu4 will result in different dispositions of these different atoms. Okay, and that is how we call this as C3 prime endo, and etc., 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 all of these. And there are in between things that are, T is a twisted conformation, where T means there is both the two atoms, C2 prime, C3 prime endo, one above, one above, below. It generates in that sort of a conformation. You have endo conformation, exo conformations, and twisted conformations. In endo and exo conformation, 4 atoms are in the plane, 1 atom is above. Okay, when we say C4 prime exo, all the other 4 atoms are in the plane and C4 prime is on exo position. If I take O4 prime endo, all other 4 atoms are in the plane and O4 prime atom is towards the C prime end. Okay, when I write only exo, endo and things like that, that means that particular atom alone is outside the plane and all other 4 atoms are in the same plane. When I say T, it means it is a twisted conformation. That means 2 atoms are outside the plane. Okay, 2 atoms are outside the plane, one is above the plane, one is below the plane. And that the whole set of conformations are therefore represented in this kind of a circle. So this is called a pseudo rotation circle. Okay, and the elements which are there below in this 0 to 360 plane. So once we take the equator down here at this 90 degree, O4, so O4 prime endo, these are exactly opposite to each other. Okay, O4 prime endo means O4 prime is on the above the plane, O4 prime exo means it is O4 prime is below the plane. Okay, so these are exactly opposite ones, and those are the conformations are represented by E. Endo exo represented by E, and if one atom is above, one atom is below, they are represented by T. That is called as twisted conformations. Okay, the ones which are below, so schematically or conventionally one calls them as the south conformation. The ones which are from here to here, these are called as S conformations. The ones which are from here to here, these are called as N conformations. Okay, that is represented here. S conformations and N conformations. Okay, so this is the definitions of the sugar ring, how it happens. So therefore, sugar ring plays quite an important role in determining the geometry of the DNA. What is the structure of the DNA? Okay, and by and large, one is observed that in B-type DNA, different kinds of DNA structures are possible. In B-type DNA, you have mostly S conformations, and in RNA, you have the N conformations, by and large. Okay, but there is also A DNA. When you have A DNA, then of course you also have the N conformations. That also is possible. Okay. Now there is one more torsion angle which is important, and that is called as the glycostatic torsion angle. The glycostatic torsion angle determines how the base is oriented with respect to the base, with respect to the sugar ring. So here I have indicated the base is here. Okay. Now in this situation, the base is attached at the base is at the C1 prime position here, okay? And here I have shown what is the purine ring. The particular, which purine ring it is? This is A, okay? The C1 prime is attached to the N9. This is the N9 position, okay? Of the purine. In the 5-membered ring, the nitrogen which is present, this is 9 position. The C1 prime is attached to the nitrogen, that is the 9, N9, okay? This is 7, this is 8, this is 9. Attached to the night at this position, and this is 6. Now you look at the orientation, the position of this ring with respect to the sugar ring. Notice here in this particular case, the 5-membered ring is towards the sugar ring, towards the DNA backbone chain on the 5 prime side here, and the 6-membered ring is outside on the other side. Okay, this is outside here. In this situation, the 6-membered ring is inside on this side and the 5-membered ring is outside. Okay, that is just you make it 180 degrees rotation. With respect to this torsion angle, you make a 180 degrees rotation, it goes on to the other side. It is present here, you rotate it by 180 degrees, then this will come on this side. That is what is here. Okay, and these two are defined as different conformations. This is called as the NT conformation, this is called as the SIN conformation. Two different kinds of conformations are possible in the case of base orientation with respect to the sugar ring. And that is explicitly shown here with a ball and stick diagram here. And this is the sugar ring. This is the sugar ring here. A C2 prime endo sugar pucker. The C2 prime atom is up here. And the sugar is and the base is attached here. And you notice where this is the guanine. In this case, it was the adenine. Here it is the guanine. And then NH2 group, the 6-membered ring is down here. The NH2 is oriented in this manner. In the case of, and which is this conformation? C2 prime endo sugar pucker. This is the NT conformation, right? Because the 6-membered ring is outside. Outside is not towards the sugar ring, is on the other side. This is the NT conformation. The NT composition of guanine. And in this, the 6-membered ring is come on this side, on top of the sugar ring. Okay, this is called as the SIN conformation of the sugar ring. Okay, why does this become important? You will see here, then depending upon what we have, you have different distances between the hydrogen atoms. The hydrogen atoms which are going to monitor in our spectra, they have different dispositions. The relative distances of the hydrogens. There is a hydrogen here and there is a hydrogen here. Okay, the distance between these two is one thing in this situation, and the distance between that is very different in this situation. Okay, this is so far here compared to this is the C3 prime endo sugar. Because this particular hydrogen atom is here, this is very far away. So therefore, in these situations, these distances matter, and you will see them in the NMR spectra. You will see, depending upon the distances what we have, you have different kinds of correlations in the NMR spectra, which you have discussed before, right? We have discussed the nosy, cozy, and all of those ones. And these matter. And this is what we are going to use. That is why I am describing this to you in such great detail with respect to the nomenclature. Which atom number is what is where, which hydrogen atom, which carbon atom, which nitrogen atom. All of these things are important, and you have to keep looking at these numbering schemes again and again to understand and analyze the NMR spectrum. Okay, so this is the glycosidic torsion angle. Okay, now you see the appearances of the structures. This is a particular, now this is a single crystal structure, okay? This is not the fiber diffraction anymore. This is now a single crystal structure, shows the atomic details. Atomic details of the individual atoms. This is the oligonucleotide which is used here is GGTATACC. This is the 8-mer DNA sequence, and this is crystallized in the form of an aDNA. Okay, this is an aDNA structure. aDNA structure you see is a fat compared to the B. I will show the bDNA also. This is fat here, and this has shallow minor groove is frontal at the top and the very deep major groove. So okay, we can see that in other pictures there. Okay. Opening of the major groove. Okay, so this is the classic stereo picture of the, and all these pink ones are the base pairs. The black is the backbone. The two chains are running like this. One is running like this, other one is running like this. This is one chain, other one is like this. Okay. So this is like this, and the other one is like this. So these two chains are running in this manner. This is the aDNA. Look, remember this aDNA, how it looks. It looks fat. And this is bDNA. Very slim. This bDNA is very slim. This is the stereo picture again. Okay. And now this is the different sequence here. CCAACGTTGG. So this is how many years? This is 4 to 6 plus 4, 10 mer sequence. And this is a single crystal structure. Single crystal structure, all atomic details are there, and the model is built. So very clearly you can see how the two chains are running. chains are running here, and the base pairs are held together. Here, bases are held together, forming base pairs, and the structure is very slim here. Now, the number of units which are going from one end to the other end, that is one complete turn of the DNA, is different in the two cases. Different in the case of bDNA and aDNA. That also, and that those are all the parameters one has to list, one has to understand. Here is a physical picture, appearance of the two DNA structures, aDNA and bDNA. Now, this is another DNA which was discovered in the late 70s. This is the 1979. Very interesting. This is called as the ZDNA. In the other two cases, both aDNA and bDNA, you see the helices were going like this. One helix going like that, other one is in the opposite direction coming like this. Now, these are right-handed DNAs. These helices are right-handed. The turn is right-handed helix. Both are right-handed helices. Okay, and they run in opposite directions. Okay, 5 prime to 3 prime and 5 prime and 3 prime to 5 prime. One end is 5 prime, other one end is 3. So in both cases, both aDNA and bDNA, that is the situation. But this one here, this is the ZDNA. Okay, so now this one is of a hexamer. This is CG. 6-mer DNA. Here it is zigzag. That's why it is called as ZDNA. It doesn't have very clear helical structure. It is a zigzag structure. And the two chains here are not anti-parallel. They are parallel. These are parallel stranded structures here. And the repeating unit is not one. Earlier we described 6 torsion angles along the backbone. The same thing repeats. One nucleotide repeats. But here it is actually 2 nucleotides repeat. 2 nucleotides form one unit, and those ones will repeat. So structure of the 2 units will have to be described here in order to describe the structure of the ZDNA. And this is not so naturally occurring DNA, but this was created in a particular condition, experimental condition. This was observed. But of course, the biological significance of this is not very clear. How much is present in the natural DNA, we don't know. Because of course, we don't understand the complete DNA yet. Okay. As I said, we only know 5% of the DNA. What is the 95% of the DNA doing? We don't know. Whether such structures exist in that, whether such structures are responsible for any abnormalities. So we do not know. But it is quite possible. There is a variability. Variable structures are possible, and whole lot of structural information is required in all of these cases. Here, 2 units form one repeating unit. Okay, 2 nucleotides form a repeating unit. In both aDNA and bDNA, there was 1 nucleotide repeating unit. Here in ZDNA, it is 2 nucleotide repeating unit. And the 2 individual nucleotides in the repeating unit have different structures. Okay, and that we will see in more detail here. Okay, now these are the various torsion angles which are listed here. Alpha, beta, gamma, delta, epsilon, xi, and chi. And these alpha, beta, gamma, delta, epsilon, chi, these 6 torsion angles are along the backbone, and chi is in the glycostatic torsion angle. Okay, you see there are so many different DNA sequences which are listed here, and some of them have come from the fiber diffraction data, and some of them have come from the single crystal. Incidentally, in the early phases, the DNA structure, it was not possible to obtain single crystals. All the previous structures were all from fiber diffraction data. Okay, the A and A which is given here, see this and this listed here, these are from the fiber diffraction data. What you have there information is only the symmetry and the repetitive information. What is the symmetry in the structure? On the basis of that, you build the model. You have not looked at the individual atoms in detail there because the resolution is not there. Fiber diffraction doesn't provide you that. Then when you have the single crystals, then of course you have the atomic details. Then your more high resolution structures are possible. Then you can see the numbers have changed somewhat. By and large, they are in the same range, but the numbers have changed somewhat. bDNA, this is my aDNA is minus 50, bDNA is 41 here, and in this structure it is minus 75. The alpha is minus 75 in this structure, and this is 185. This is 136. 56, 38, these two are close. This is 56, 79, 91, 139, okay, minus 146, minus 166, minus 133. Okay, so you can see, and these ones are in the anti-domain. These structures are in the anti-domain of the torsion angles. Now, and this was the first longest DNA sequence whose X-ray crystal structure was determined. This is called the Dickerson model. This is the Dickerson structure. He was the first one to determine the structure of a long DNA sequence. Long means 12 is already quite long. To get the crystals of this was very difficult, but they managed to get the crystal of this along 12-mer DNA sequence, and with that they got the high resolution structure of this. And they gave you minus 63, 171, 54, 123, minus 169, minus 108, minus 117. And these are the ones which are by and large used for describing the bDNA. Now we come to zDNA. Now you see I have to list two here, C residues and G residues. As I said, two nucleotides form the repeating unit here. And each of the nucleotide unit has different kinds of conformations. And the values of torsion angle there. See, for the individual repeating unit, for the C residues, you have this angle here, minus 137, minus 139, 56, 138, minus 95, 80, minus 159. And for G residues, 47, 179, minus 169, 99, minus 104, minus 69, 68. Okay, and then there is a DNA RNA decamer. Then they made a hybrid here. Let's not go into that one. And the ARNA is more like the aDNA. Okay, so that is very similar to the aDNA here. This is very similar to that. So by and large, RNA is in the A form. aDNA is special, but normal for DNA is B form. Okay, Z form is special, and this is the bDNA. This structure is bDNA. Okay. And this structure is RNA structure, and you will find the same thing in the aDNA also. Okay, these are typically the average torsion angles for DNA helices. And these are in the anti-conformation. All of these are in anti-conformation except this. See, this fellow, the glycosidic torsion angle is in the syn conformation. And all other ones are anti. In the anti-domain. Glycosidic torsion angle is in the anti-domain. Except for this, in the CG unit, zDNA, this G unit is in syn conformation. And this also has the sugar ring in the C3' endogeometry. Okay. For the G residues, this is the C3' endogeometry. And other ones are all C2' endogeometry. The delta angle giving this is the C2' endogeometry. And here this is again aDNA kind of a thing. This is C3' endogeometry. The RNA kind of a structure. Okay. So by and large, these are the parameters which are obtained from the single crystal data. Okay, now the next thing we have to look at is the base pairs. So we looked at the backbone torsion angles, we look at the glycosidic torsion angles, and then we have to see what are the base pairs. How are the base pairs oriented with respect to each other? We have the bases, there are two bases in each base pair. How are these bases are oriented with respect to each other? Are they all exactly in the same plane, or they are twisted with respect to one another? They are. What is the relative orientation of those of the two bases in the base pair? So this is an important information which will determine whether the DNA will curve, okay, whether it is forms a go in like a cylinder, in a straight cylinder, or it forms a curve. We do not know. So all of these parameters will describe that. So what are the parameters which are important here? So let's look at this. So this is a particular base pair. So this is represented in the base pair here. Now the coordinate axis given by the red lines there. Now if they are, this is the z-axis. The z-axis is the axis which goes through the length of the DNA sequence. Okay. The other two axes orthogonal to that are the xy planes. In the xy planes, you have along the length of the DNA, it is called as the rise. How much is the distance between two base pairs is called as the rise. From one base pair to the other base pair is called as the rise. And the other sides, you have the with respect to the other parameters which are there. Now, within the individual base pair, let us look at how the base pair is oriented with respect to the individual axis. So here you see what is shown here. This is with respect to this, there is a rotation here. With respect to this axis, the base pair is tilted. Okay. We kept both the things in the same plane, but just the plane is tilted. The plane is tilted like this. Therefore, this is called as the inclination here, and here it is called as the tip. this rotation is along this axis rotation, because we have the three axes, right? Z-axis we forget. Z-axis is the length of the DNA, and the two XY axis, you consider rotations around the two axes. One rotation angle, this rotation gives you the tip, which is called as the theta, and the rotation with respect to the other axis is called as the inclination, which is represented by eta. Now, here we consider the two bases are in the same plane, but they need not be exactly, okay, they can be different. And now when that happens, you will generate other possibilities here. Here the two base pairs are opened with respect to each other by a certain angle, which is called as the sigma. Now here they are twisted with respect to one another along one of the axes, and that is called as the propeller. So one base is here, other base is twisted with respect to that, that is called as the propeller. If you consider that with respect to another axis, then we call as the buckle. See, these are basically with respect to the individual Cartesian coordinates. With respect to the individual Cartesian coordinates, how are they displaced? And that is the different parameters which describe that. This is called as the buckle. Now here it is, now we consider two base pairs, two neighboring base pairs. How are the two neighboring base pairs placed with respect to one another? Here the two neighboring base pairs are parallel, but they are twisted with respect to one another. One is like this, other one is like that. And that is called as the twist. Now in the second case, the roll, one base pair is like this, other one is oriented like this with respect to that. So there is a roll. It's not exactly parallel on top of each other, but it makes a certain angle. It makes a certain angle, you can draw an angle there. So that is called as the roll. Now with respect to the other axis, the same kind of a roll you call as the tilt. One angle, one axis you call it as the roll, other axis you call as the tilt. Okay, so therefore, what are the parameters here? With respect to the individual base pair, how are they displaced in the with respect to the two axes, torsion angles, not torsion angles, the XY coordinates, okay, and within the base pair, how they are, whether they are in the same plane or are separated out with respect to one another in the base pair, that defines one set of parameters. And then when you consider two consecutive base pairs, whether they are parallel to each other or tilted with respect to each other, and this still can be with respect to the different axes, and therefore then we call as two different torsion angles, two different orientations. Then you also have the rise. The rise is from one base pair to another base pair. How much is the rise along the z-axis? And that is called as the rise, dz. And slide. Slide means how are they separated from the center of the base pair? Whether they are whether the z-axis goes through the center of each base pair in every case, or does it change? Need not go, no. So you draw an axis, vertical axis, but there are 12 base pairs or 10 base pairs. In every case, the vertical axis need not go through the center. It may go on, in one case it may go through the center, it may be slightly shifted towards the x-axis, or it may be slightly shifted to the y-axis, and accordingly we call them as different kinds of shifts. You have the shift dx or the slide dy. So these are the different parameters which are there. Then on one side you have the so-called major groove, other one side is called as the minor groove. On top of this you have the major groove and the minor groove. So these are grooves which are there in the DNA. Their groove sizes and the widths can also change depending upon whether there is bDNA or aDNA or RNA, so on and so forth. So the z-axis is called as the helix axis. With respect to the helix axis, so I'm just repeating that once more. With respect to the helix axis, how are the individual base pairs placed? Does the helix axis pass through the center of the base pair in every case, or passes through it is shifted from the center of the base pair in some way, either along the x-axis or along the y-axis, and that determines the so-called shift. Okay, so now these are those parameters which are there here. You can see, and all subtle variations have been found in various kinds of DNA structures, and these are based on the crystal structures, single crystal structures, various parameters. Now, here also it is said here, Another thing, the Z DNA is actually left-handed DNA, left-handed helices, whereas all other helices, the A DNA and the B DNA, these are right-handed structures, and the Z DNA is left-handed structure. Okay, the left-handed but the helix sense goes in that manner. Considering two repeat units, 2 units of the repeat, it goes in the left-handed sense, and that is one difference. And here it is telling you the number of residues per turn. See, the DNA has, typically the B DNA has 10 units per turn. A DNA has 11 units per turn. And this particular structure, which was also had 11 units per turn. And the Dickerson structure, which was there, this had 9.7 units per turn. And C DNA is 9.3, D DNA is 8, and Z DNA has 12. ARNA has 11 units, A prime RNA has 11. So these deviations occur slightly in the combinations of the various torsion angles. The conditions play a very important role in defining the structures of the individual DNAs. And also here the groove definitions are given. What is the groove width? How much is the width of the groove? We can calculate from across one atom to another atom. There is a definition there which is given. You can see what is the width of the groove. In the minor groove, how much is the width? In the major groove, how much is the width? Okay, and that distances are given. Okay, and groove width, depth. So these are the various parameters which define the topology of the DNA structures. Okay. Okay. Another thing I point out here, the Z DNA I mentioned to you. You have the G unit had C3 prime endo and syn conformation for one of the nucleotide units. The other one nucleotide unit was, of course, the same as the C2 prime endo and NT conformation. Okay. Now these are the parameters for the base step. In B and A DNA, there is a base step, there is only one single unit step one has to consider, right? So because nucleotide repeating unit is one repeating unit only, one nucleotide unit only. Therefore, for B and A DNA, there is at every step, this is what it is. Various parameters are given, 36.1. So typically we know 10.4 turns per units per turn. That's the typical thing for the BDNA. That's what one often uses. And in the case of CG step, in the case of ZDNA, you have the CG and the GC. These two are different. Okay, and the various parameters which are given here, we don't have to remember all of these things, but when you actually want to determine the structure, you can see where do they belong, what are the parameters which you get. You can describe your structure in detail in terms of this. Whenever you determine the structure, it is you have to deposit in the BMRB or the PDB. You'll have to provide all of these, all the parameters. The base step parameters. Base step means, and then the base pair parameters. Base pairs are within the same base pair. This is the base step parameters from one base pair to another base pair. How much are, so I described to you all of these parameters earlier, and these are the numbers with regard to that obtained from the X-ray structures. BDNA, ADNA, and BDNA crystal structures, and for a model of a ZDNA helix. Okay. So now this is the ZDNA, BDNA and ZDNA comparison here. You can see here, you cannot see the grooves very clearly in the case of ZDNA. Whereas in BDNA, you can see these clear grooves. There is a groove here and this big groove there. This is the minor groove and this is the major groove. The one which is present here. This place, this is called the major groove. This is a right-handed helix which is going, and then this is the minor groove, small groove between the two helical chains. There is one chain going like this, other chain coming like this. Between these two, that groove, that is called as the minor groove. And then the major groove is within the this chain only. The chain is going like this, other chain is going like this. This is a major, this is a right-handed helix, this is the major groove. You can see that this is the larger one. And that is called as the major groove, and this small thing is called as the minor groove. Whereas in this case, the grooves are not very clear. In the ZDNA, things are not very clear. It is a left-handed helix, and the grooves are deep, and it's not very clear. And it is slim. This ZDNA is much slimmer than the BDNA structure. Typically, it is observed that ZDNA structure is often found where you have GC-rich regions, CG-rich regions. And often we see that various DNA sequences which are very susceptible to diseases, and the transformations that happen, they happen in the CG island. Those are called CG islands. Okay, in those areas only you get a larger number of aberrations. Yeah. Okay. You can even look at this carefully, how the chain runs. See, the chain is running like this, 2 units, and here it is clear, it goes like that. Okay. And the other one comes like this. Yeah. So okay, now so much for the topologies of the structures. Now we'll come to a little bit more intricate details of this. The base pairs which you mentioned. So far we talked about the Watson-Crick base pair. Those were the base pairs with which they built the model. BDNA model was built, and the ADNA model was also built. Crystal structures were determined, and they all agreed with the what proposals which had made by Watson and Crick. Now, we said, is that the only way we can make base pairs? No, there are many different ways you can make base pairs. So, purine pyrimidine base pairs. Here, for example, Watson-Crick was the one, this is the original one which was given. This is the Watson-Crick model. 2 base pairs in the case of AU or AT, and 2 hydrogen bonds in AU or AT, and 3 hydrogen bonds in GC. And the particular way the hydrogen bonds are made are indicated here. Okay, now notice here, this is the 6-membered ring of A is bonded to the 6-membered ring of the U in the AU base pairs. And similarly, in the case of this one is, now this is, okay, this is G here, this is AU and this is GC. In the case of GC also, the 6-membered ring of the G is involved in the base pairing with the 6-membered ring of C. This is in the Watson-Crick. Now, in the case of, there is a reverse Watson-Crick. Reverse Watson-Crick also, it is the same 6-membered rings which are involved, but it is the different atoms which are involved in the hydrogen bond. For example, you see here in this GC, this oxygen is involved in the hydrogen bond formation here. In this case, this oxygen is not involved in the hydrogen bond. The NH2 group which is present here has come down here. The oxygen of this, that is the oxygen of this, is switched to the other side. This has come down, and this oxygen here which has gone up here, and this forms a hydrogen bond here. So therefore, in this case, the GC hydrogen bond also has GC pair also has 2 hydrogen bonds. AU has 2 hydrogen bonds, GC also has 2 hydrogen bonds. This is perfectly possible. And the switching of this means the glycosidic torsion angle would change. Because this torsion angle, this glycosidic torsion angle is here at this point, and that will switch. And when that happens, you will have a different kind of hydrogen bond there. This is called as the reverse Watson-Crick. Okay. Then you have the so-called Hookstein pairing. Hookstein pairing means here the 5-membered ring of the purine. See here, this is the 5-membered ring. That was not involved. This was outside here. In this Hookstein pairing, The 5-membered ring of A is pairing with the U, is involved in the hydrogen bond. This nitrogen is involved in the hydrogen bond, and this is at the N7 position. N7 position is involved in the hydrogen bond with the U, okay, with the 6-membered ring. Same is true here for the reverse Hookstein. Why reverse Hookstein? Because it is the different oxygen which is involved. Here you see, where is the R? The R is here. This is the sugar ring. The sugar ring is here. And where is the sugar ring here? It is gone there. That is because it is a different oxygen. Here it is this oxygen. In this case, this oxygen is come up and that is involved in the hydrogen bond. So the NR has gone up there. NR is down here. So these NR and this NR in the same direction. Here, this NR is here. This NR is here. R is the ribose ring. Okay, they are in opposite direction, opposite places with respect to the base pair. And this is called as AU reverse Hookstein. The Hookstein was one person who actually also proposed a model for the DNA structure, but it turned out that that was not what was observed in the crystal structure, fiber structure, which fitted the model of the fiber diffraction data. Therefore, that got eliminated. That does not mean that this never happens. This does happen in various places, different situations. All various kinds of hydrogen bond schemes are possible, and they will happen. How do you know they will happen? Okay, let us think of it this way. The DNA chain so far we considered is going in a linear manner. It goes from one direction from here to here, let's say. And how much is the length of this? We said the rise is about, for the bDNA, 3.4 angstroms per base pair. From one base pair to next base pair is 3.4 angstroms. Now a complete cycle is 10 base pairs, so about 34 angstroms. 34 angstroms is one complete turn of the DNA. One complete turn, then the next turn starts, and the next turn, it goes like that. And this is 10 base pairs. Huh? And now how many base pairs are there in the genome? 10 to the power 9, 1 billion. So 1 billion. So 34 angstroms into almost 1 billion, or one fraction of one order long, 10 to the power 8 you take. 34 into 10 to the power 8, that means 34 centimeters. 34 centimeters will be the length of the linear DNA if we have to do that. If it is completely linear, it will be 34 centimeters long, and sometimes even more. It can go into a meter. How is that packed inside a cell which is a micron size? That means the DNA must be folding left and right, all over the place. It can be folding at various places. Okay, when that happens, we cannot stop formation of such kind of hydrogen bonds. There will be various kinds of interactions possible. So such kinds of interactions can happen. Now likewise there are also so-called wobble base pairs, GU wobble base pairs, GU reverse wobble base pair, AC reverse Hookstein, AC reverse Hookstein. You have earlier we talked about AU base pair, right? AU, A pairs with U. But here we see G pairs with U. This is called as wobble. G pairing with U is called as wobble. This is not common, and therefore it is called as the wobble. The wobble space also can be formed. GU wobble, GU reverse wobble. And similarly AC. A pairs with T always, by and large, in the bDNA. But A also can pair with C. That's also possible here. You can see here AC reverse Hookstein and AC reverse wobble. So you can have this kind of base pairing process.
To unlock your iPhone first.
What is it? I didn't do anything. Okay, so therefore AC base pairing is also possible. AC, and also two different ways. And AC reverse Hookstein and GU is possible. Similarly, you can also have a T's, AT and AC and things like that. AT to normal, so you can have AU and GU. So these both are possible. So this is the pyrimidine base pairs. Now you can also homopurine base pairs. There is purine base pairs. So you see here AA, there are two A's, one A, another A here. One A, another A here. And they can also form base pairs. The NH2 of this is involved with the N of 1. NH2 of one is to the nitrogen here and the nitrogen here. Okay, this is symmetrically placed. They are perfectly possible. And this is the AAN1 amino symmetric, AAN7 amino symmetric. Here you are using what? You are using N6 and N1. Okay, here you are using N7 and N6. Okay, so therefore you are using the amino and also the nitrogen at the 7th position. Here you use the nitrogen at 1 position and here you use the nitrogen at 7th position. Therefore this is called as AAN7. Now we can also have the third possibility, AA, where that is N1 amino and N7 amino. We can have amino hydrogen bonding, AA. Amino, there is amino, NHN hydrogen bond, NHN hydrogen bond. And similarly, you can have the GG, N1 carbonyl symmetric. This is N1 there. You can have base pairs with the carbonyl here and N1 to the carbonyl there. This is NHO hydrogen bond here. N1 carbonyl. GG, N3 amino symmetric. Now you are using the N3 here. N3 is forming to the amino here, which is at 2 position, and N3 is to the 2 position here. So this is N3, both these are symmetric. Then you can have asymmetric ones, GG, N7, N1, the carbonyl amino, that is the carbonyl of 1G, it goes through the amino or hydrogen of the other one, and there is one hydrogen bond, and the second one is NHN. The N7 goes to N1. N7 goes to N1 of G. N7 of 1G goes to N1 of other G. And N1 has a hydrogen, N7 has no hydrogen. And therefore, this hydrogen bond is possible. GG, N1 carbonyl, N7 amino. This is, and so many possibilities exist here. So this carbonyl forms with the N1 hydrogen here, and the amino here goes to the N7 of this guanine here. So this is only to the, when you have to draw these out structures, you will realize that okay, there are so many different possibilities, and one has to investigate in experimental data as to what sort of hydrogen bond is present in your structure. And that you can only do when you understand the individual possibilities, the nomenclatures, and the signals of the individual protons. You have to monitor the individual protons in your structures. So then you can have heteropurine. So the previous one was homopurine, that is A to A and G to G. You can also have heteropurine, that is A to G and A to G base pairs are also possible, and different possibilities. GA N1, GA N3 amino N1. Okay, so you see here N1 is this position here. This is N1. This is N1. N1 to this one there. Both are N1, N1. Here is N3 amino to amino N1. Okay. So this is N3 amino to, this is the amino to N1. There is N3 amino, so N3 amino to amino N1, G and A. Okay, so that is a possibility. Both are between the amino group and the nitrogen. So that is the way it is. Hydrogen bonding G, A and A. Okay. So, and in this case was N7, N1. What this N7, N1 means, which hydrogen atoms, which nitrogens are used in the hydrogen bond formation. That is what is indicated there. N7 amino to N3. And both are aminos there. Okay, similarly, you can have pyrimidine base pairs, and yeah, of course, this is all jugglery. Of course, this is one cannot remember these ones, but I'm showing you all of this mainly because these are possibilities. So many different possibilities exist, and you can form different kinds of hydrogen bonds in all of these the structures. Okay, now with all of those different kinds of structures, what all different topologies of DNA can be formed? You see, these are duplexes which you have by and large seen. You can have different kinds of topologies there. You can have a stretch of the single strand, then the chain goes like this, comes down, the chain goes like this and comes down like this here. Okay, these are called single stranded regions. There are single stranded regions here, then there is a duplex region in between, then there is a loop here which is not hydrogen bonded anymore. Then you can have hairpins kind of a structure. What happened? The hairpin kind of a structure. So this is the partly you have a duplex there, and then the rest of it is a loop. Okay, this is called as a hairpin. Okay, and this is a kind of a bulge. In a duplex, at the middle there is a kind of a displacement outside the helix, then that is called as the bulge. Or this is a smaller bulge, a single base bulge. You have many bases which are going out here. This constituted the bulge. Here you can have a single base which is going out, that is called a single base bulge. And then you can have in the duplex itself, you have symmetrically placed loop bulges. Okay, so internal loops. So this is the kind of an internal loop here. Chain and then takes a loop, comes back again. Here chain goes, takes a loop and comes here again. So duplex combined with kind of a bulges that forms as internal loops. So symmetric internal loop, anti-symmetric internal loop. Okay, so this is this anti-symmetric means these two loops are not identical. Here the two loops are identical. In this and this they are identical. Here these two are not identical. And there is a three-stem structure. So you have one stem here, the second stem here, and the third stem there. Three stems are present and these are forming a structure together. So the DNA can go in various ways. Okay, then you can have a four-stem structure. See, there are one stem, second stem, third stem, fourth stem, and there is a loop here in the middle. There is a four-stem structure. You will find all of these structures experimentally. I will show you those. I will show you some of those, the kind of structures. How many more I have? Let me see. Okay, this is almost done. Almost done. So only two more. That's it. Okay, after these rules. Now you can also have what are called as base triples. Base triples, you have the base pair. Now you can also have a third base coming here and binding to this base pair itself. There is one base pair, 80 base pair here, and the third base comes and pairs here. So therefore, this can form a so-called a triple-stranded structure. Because now you have three bases hydrogen bonding. You have the normal 80 base pairing, then you have another T which is coming here. So therefore T80, this is called the T80 base triple. Similarly, you can have a CGC base triple. GC base pairing, then you have this individual, another C coming in there, and you have this person. Now what is all these double arrows which I have drawn here, these are to indicate the hydrogens, which one would like to monitor. Okay, these are the hydrogens which are observable in the immunoproton spectra of the DNA, and you can monitor their progression and distances between them, and so to determine the structure of the triple helices. Then you can also have four bases organizing. You see, here there are triples. Now here there is a four base. There are four Gs. 1, 2, 3, 4. 4 Gs. And between these Gs, there are two hydrogen bonds. Every two Gs, there are two hydrogen bonds. So you see such a beautiful structure which is formed. This is called as the G tetrad. G tetrad. There are four Gs arranged in a particular way, and they form base pairing network, and the base pairing network is indicated here. Very symmetrically placed with respect to one another, and the base pairs, the hydrogen bond scheme is also very symmetrical. This is called as the G tetrad. Okay, now this is the DNA triple helix, show the structure of the triple helix, how it is formed, and the green one here is your normal duplex DNA. Green is a normal duplex DNA. And the third strand is coming in this major groove of the DNA. It's coming in the major groove of the DNA and interacting with the base pair from outside. Okay, as I shown you there. In this, see the coming here and it is in the major groove. Okay, this side is the minor groove of the DNA. This is the minor groove and this is the major groove. In the major groove, it is coming and binding with the base pair through two hydrogen bonds. Therefore, all the third strand always comes in the major groove of the duplex DNA. And the red strand is the third strand. And how does it come? See, the duplex goes 5 prime to 3, 5 prime to 3 prime here, and the 5 prime to 3 prime here. And the third strand obviously has to be parallel to one of those. When it goes in the major groove, it is parallel to this 5 prime to 3 prime strand. So this also goes 5 prime to 3 prime, and it pairs with the base pairs which are already there in that one. So this is how the DNA triplexes can be formed. DNA quadruplexes is formed, then all kinds of junctions and the branching and all sorts of structures are possible in the DNA structure overall. And that is how the DNA gets packed inside the cell, which is so small in size. Okay, I think recombination or triplex. This is the indication of how the triplex DNA is formed with this particular one. You have the Watson-Crick base pair here. The W strand, the C strand are the two duplex strands, duplex DNA strands. That is the pink and the green. These are the and the brown and the green. Brown and the green are the Watson-Crick duplex, and the pink which is coming as the third strand, and that is in the triplex. I still have so much. Now you can have Watson-Crick base pairing the C plus GC TAT. I think we will stop here. This is getting too much. So we will continue with this in the next class.
So Friday, 3:30.
Yeah. We'll stop there and we will continue from there.
So
Yeah.
is there any question, any doubt? One question.
Transformation takes place with the ages or remain the same. Well, the DNA does get transformed, and that is because of the environmental factor. That is called the epigenetic transformation. That depends upon the environment, the diet you eat. There will be mutations inside the DNA, and these are called as epigenetic mutations. Okay, it's not necessarily with aging. It has to do with the environment. Was that clear? Any other? Is that clear? And those are called as mutations, okay? Epigenetic mutations. Anything else?
मैं एक दिन से बोल रहा हूँ तो ड्रॉप है ना अभी प्रोफेसर का कंज्यूमर एजुकेट नहीं अच्छा आपने जो पिक्चर स्क्रीन का है बस
End the meeting, yeah.
पूरा